architects, Douglas Moore, was the chief architect at Sapient way back in the 90s. A long time ago. Betraying our age and experience.
Unaccepted people often are discoverers. Or any
We've met a couple times with Sheldon and some of the other folks. Sapient, different discussions over the years, like potentially partnering or what have you. Yeah, still, I think they've done a great job. I mean, they're unique in being a survivor and thriving out of the class of agile consultancies, client-server consultancies from the 90s. They're still in business and growing.
I'm pretty impressed that they shifted their attention to front end.
You bet.
So I mean, you have to know which problem. I mean, you can't just want an all solution. You have to know what you want to do. I mean, it's useful. You just have to know when to use it. When it makes sense.
Is it working? Is it on?
So it's kind of like anomaly detection. So you have to use a lot of.
For what purpose?
A lot of data.
About names and things like that. I'm trying to figure out to see. I'm trying to understand how big data can go and captures maybe some patterns or see some trends that people are not seeing before they commit fraud or while they're doing their fraud or cheating. No, I'm not. But the insurance that I'm in, it's really there's a lot of data. So big data has to be good. Like the statistics game is good, but if you want to figure out where big data can tell us where the fraud's happening, that's going to help a lot.
It doesn't have to be a lot of improvement to be worth a lot.
Yeah, just 1% phenomenal. That's where it happens.
And you bring up a good point because there's always an issue of false positives.
What is the guys' connection with factual?
Really, they just invited us to speak, to present on Storm, and we thought it would be a good opportunity to come down and talk a little bit about it. We've had some experience. No other connection with Factual specifically. I think mostly they host the meetup. Subhash works at Factual, is that right?
It just so happens that maybe they fall into that bucket.
Have you been to these meetups before? Yeah. What other topics have been presented recently? Okay.
Well, that's the thing. So what they did was they got reported, they manually went into a scenario and they saw their assumptions. And then that was good.
How do you think data will fit you guys in their overall journey?
I think they have a strategy in terms of integrating open source platforms, Hadoop, with more traditional data warehouse technologies. So we have a lot of demand in the open source platform space. It's really bringing more competency. Lots of customers want help on how to really use this stuff. What's practical? How do you integrate it into the architecture? Start to get business value. So it's pretty much what we've been doing, but now there's a lot more customers, a lot more resources to build up and do more in this space. So it's sort of doing a lot more of what we have been doing, which is a good thing. So, our total, it's a little under 100 right now that continue to ramp. So we have solutions led by consulting, but then we also have an R&D team that build kind of reusable components and support that on top of it. The big thing, of course, there's open source platforms, but building repeatable assets that work on top.
Have any portfolio managers approached you for requests for solutions?
We actually, well, we've got one private equity firm that we're talking to.
Because I can only imagine it just logically. Like, I don't know
So guys,
exactly.
we're gonna get started. For those of you who are in the kitchen, we're gonna get started. Come on down and have a seat.
We've done some work with hedge funds too.
So thanks again once again for coming. Today we have a great presentation. Before we get started, just a few announcements. So first, I would like to thank Factual for hosting and providing us a delicious dinner. So Aaron, thank you again for hosting. Round of applause for Factual, if you don't mind. So just a few quick announcements. September 25th, we have a Hug meetup. It's going to be on Hadoop private virtual clouds. It's going to be up at cross campus, so take a look at the meetup page. September 30th is the Spark meetup group. It's our first Spark meetup, and it's going to be a panel of Spark speakers. So we have Sandy Reiser from Cloudera, Sumbu Q from Appar, and Kelly Bond from Tuple. It'll be a great talk and discussion on Spark, the future of Spark. So sign up for that. Again, it's all free. And with that, I would like to introduce Ron Bodkin, CEO of Think Big Analytics, Teradata company. So they were recently acquired by Teradata, and Ron has graciously agreed to present today's topic, which is on Storm. So without further ado, I'll hand the microphone to Ron. Round of applause, one, please.
Thanks, Josh. Yeah, definitely great to be here and have a chance to talk to you. Just a little bit about our company. We started Think Big a little over 4 years ago, always with the mission of really helping organizations get measurable value from big data technologies that do NoSQL, more recently streaming technologies like Storm that we're going to talk about tonight, as well as being able to help with consultation, what are the strategy, what are the ways that you apply these technologies, and then engineering, building systems and solutions that build the big data applications as well as data science predictive models. So, it's our experience has been helping organizations of all sizes over the last 4 years applying big data technologies. And I'll talk a little bit about some of what we've done with Storm. We did our first project with the technology about 2 years ago with an ad tech startup and have used it for different customers since then, including in financial services. So we've had a chance to use it in a few places. And we certainly see that there's a lot of interest in these kind of streaming real-time technologies. I Think Big, as Subhash mentioned, we recently joined the Teradata family, and we're continuing our mission to work on these open source platforms, but now with the backing of a global leader in analytics. Teradata has a tremendous depth of experience in data warehouse and data discovery platforms with Teradata and Astrodata, but recognize that this new world of open source technology, they needed a lot more capability, and that's where we come in, right? So we're going to continue doing what we're doing with just a lot more investment, a lot more ramping and growth. So I guess I'd be remiss if I didn't say we are hiring as well as getting on with the main presentation. So first thing, who's familiar with Storm here? All right, so pretty good. Who's pretty new to it? All right, so it's a good mix. So I'll give a refresher. What's a little bit about Storm if you're new to the technology. If not, it would be a refresher. I'll talk a little bit about when it's appropriate, some of the different ways of working with it, and then I'll spend most of the talk really talking about some use cases. What are areas where it might apply? So overall, you can think of Storm as a way of processing, setting up a directed acyclic graph to process never-ending streams of data. So a little bit, you might think of it as something like taking the MapReduce programming paradigm. Who's familiar with MapReduce? Who's not? All right, the very few who would put up their hands, probably a few others usually won't admit it. But so it's this idea that you can take data and shred it and have key values and be able to have an assembly of one processing step that takes things and feeds it to the next one, where you can distribute partitioning certain sets of keys, so you can do things like collecting keys together for grouping and joining, right? So Storm has in that way, somewhat like a streaming MapReduce system where you're continuously processing one tuple at a time, one event at a time. There's this notion of spouts that emit data into the system to be processed, and then bolts, whose job is to do a processing of things, a tuple at a time, and then a bolt can either pass something on to another bolt, or it can, be done with it, which often means that it produces some kind of an output that's external to the Storm system. So that's a little bit about Storm. It's open source. It was created by a company that Twitter acquired called Backtype by Nathan Mars. Continued to be developed by Twitter, and it went from a purely community-supported project to earlier this year starting to have Hortonworks providing commercial support as part of their distribution and having investment by Taylor Getz, among others, at Hortonworks. So it's now crossed over to having a commercial support model as well. Commercial in the sense that it's good pay for the support. It's still open source. It offers reliable semantics, so you can have guaranteed at once delivery in basic Storm, and there's a way to get exactly once that we'll talk about. That it's implemented itself, the language of the Storm, if you were to go on and look at its core implementation, is in a JVM language called Clojure, but mostly it has a Java-friendly API as well as a number of other languages we'll talk about. It isn't a queuing technology. So one thing that's important to think about, it's often used, the spouts are often some form of queue. Probably the most popular one is Apache Kafka, which is a high volume, efficient messaging system that's an open source that LinkedIn developed. We see that as the most common source, but there's lots of options here, right? You can use RabbitMQ or a whole variety of different ways of feeding Storm. So usually Storm lets you distribute the processing from a queue, right? So it's different in that sense. A lot of times people think, well, how is this different than a queuing technology? Queues make it easy to distribute the receipt of messages, but they don't do a lot for you to say, how do I distribute the processing of large amounts of data? And that's where this kind of streaming technology comes in from Storm. Storm is not the only approach to doing streaming that's out there. I think in sort of order of importance, probably the most important competitor to Storm is Spark Streaming. It's a different kind of thing in a number of ways. I've not spent a lot of time comparing them, but it's certainly probably the number one alternative that people will consider. The summary would be, though, that Spark Streaming is more of a micro batch where it processes chunks of maybe 1,000 events at a time rather than a single event at a time. So it's not always useful for the same use cases. There's a technology out of LinkedIn called Samza that is a alternative streaming technology that works with Kafka. Has a little bit more built-in support for state, but not a lot of traction. There's some stuff out of Yahoo Labs that isn't very mature called S4. And then it's sort of an evolution on an earlier generation of technologies, complex event processing, right? So there are a bunch of commercial companies that built systems that at sort of non-big data scale did similar things to Storm to handle streaming collections of events and being able to process those. So those are some related concepts. Now, no technology is perfect. I'd say that Storm, the biggest limitations in Storm, one is that it has a notion of a static topology and cluster sizing. So you can, when you spin up a Storm cluster, you define how many different nodes are running for what purpose, but it's not elastic. It's not easy to say, oh, I've got more data flowing in, I want to add some more bolts on some new machines, and it'll just magically work. You could shut the thing down, reconfigure, and start it back up, but it's not as convenient. So it's easier to implement. You don't have to worry about dynamic rebalancing, but it makes it a little bit harder to scale your system over time. The reliability model is a little bit, there's a couple of things. One is, in order to have good reliability in Storm, it really relies on the data source, so the spout, so that if things fail, it needs to have something that's at least reliable so that it can go back and say, okay, well, I didn't read this data, so let me go rely on the spout to replay it. So that's a good fit for messaging. If you have durable spouts, then you can actually get exactly one semantics where you only process things exactly once. And then the other more minor thing is there is a control item, a control process called a Nimbus. The Nimbus's job is just to monitor all the different processes that are running and restart them. So if the Nimbus crashes, it is a single point of failure, but it's not as catastrophic as in a Hadoop 1.0 world where a job tracker would crash and nothing could run, that your system would stop processing and you'd lose all your state. If the Nimbus crashes, everything that's still up and running works, but slowly, if other things crash, it doesn't restart them. So you want to restart the Nimbus. So not a big deal. And then the other thing I think is probably the biggest critique I've heard of Storm, certainly from a host of various proprietary startups that are hoping to take it on, is the complaint that it doesn't have state sort of built in a deep way in the system. That it's distributed processing, but if you want to checkpoint your state and think about kind of a larger notion of how data flows, it's pretty low level. You can build that, but a lot of it is on you and the application programmer to do it. So that's a little bit about sort of some of the drawbacks. But of course, having an open source streaming technology is a pretty significant advance over what had been possible before. So that's the overview of Storm. Again, the core concepts in Storm, you've got a cluster. You've got, as I mentioned, a Nimbus, which is really responsible for making sure that everything is up and running. Distributed coordination is done through the Zookeeper technology, Apache Zookeeper, so that it's easy to elect leaders and make sure that you have the right behavior, and then supervisors that are responsible for making sure the computation is working. So that's how a cluster is built up. And then within that, you'll deploy a topology, which is, again, this notion of spout and bolts that do the processing. So you get streams of tuples running through here that are being processed in a topology. So a topology is something like a set of MapReduce jobs, a pipeline that process data. And then you have the ability to have certain types of groupings of streams. So you have certain ways of distributing. You can shuffle, so you can partition by a given field inside of Storm as well. Now we'll talk, this is as good a time as any to talk a little bit about Trident. So Trident is it's a higher level language for programming Storm. It's typically used to program batches of events together in a micro batch rather than a single one at a time. And with a little bit more overhead, you can have exactly once semantics. So by that I mean, it's easy to, with reliable delivery, say, well, I'm going to make sure that I at least process each event once, at least once. But it's a little bit harder to know if something crashed, did I process this thing or not, right? So oftentimes people say, well, I'm willing to accept processing something more than once, but there's cases where you don't want to do that. You want to make sure you only handle each thing once. Like if you were debiting money from an account, I don't know if you would do that with Storm. You probably don't want to be debited twice because the system crashed, right? So exactly once becomes important there, but there's more overhead. And then, it's also possible, there's a way of using Storm to actually compute distributed RPC, which is an interesting one of the use cases. Not one that we've seen as many people using, but it's one of the ones that they use at Twitter to be able to do things like have an ongoing topology where there's state being managed through a bunch of nodes, and you can go out and distribute an expensive query across them to get an answer. So that's a little bit about the fundamentals of Storm. But let's step back and say, well, what is real time, right? I mean, so if it's a real-time processing system, what does that mean anyway? Well, for most people, real time means something about low latency. Now, the first thing you might say is, well, what do you mean by latency, right? Is it how long does it take? Is it liveliness? Is it how long it takes to get an answer out of the system? The query response time, do I get an answer back for any request I make of this thing in a few milliseconds, nanoseconds, whatever? Is it how up to date, the freshness of the data? The data is getting refreshed. That I'm seeing results for things that happened within that time frame. Is it an end-to-end response that I can, from the time that some event happens, sort of see an end-to-end output from the system in that time? Right? Those are different notions of real time. You can, Storm can give you human real time latencies within this, certainly in the milliseconds range. So that there's plenty of other use cases where we'll see people talk about real time, and it turns out for them, when you've been processing data in days, that hours is real time, And if you've been processing in a few hours, a lot of times 5 minutes is real time. So that one thing is a cautionary tale is if you're talking to somebody and they tell you they want real time, don't assume that you need like streaming single tuple at a time type real time, because a lot of times that's overkill, and there's a cost for it. So it's more expensive to build a system based on Storm that's doing low level streaming than it is if you have ability to do micro batch or not so micro batch every hour and deliver a lot of business value. So that's one thing. And the other thing is, if for some bizarre reason you were looking at doing something like high frequency trading with financial instruments, Storm wouldn't be your technology either. It's not going to compete with nanosecond scale, super low latency systems for trading. But there's a lot of problems where getting up to the milliseconds latency is a good fit, even in Wall Street, right? So we'll talk about some examples of that. So that's the first thing, is real time is not a simple term, but there's a lot of different meanings, and always worth asking when people talk about real time what they really mean. And the other thing is, if you ask somebody, hey, how fast do you want this? Well, if it's free, I'd like it immediately, right? But it's not free. So what does it mean if it's not immediately, right? It's always worth pushing a little bit on, how fast, what happens if you get it 5 minutes late? What's the impact? Oh, that's probably fine. Or no, that's a disaster. We'd lose $1 million in our trading system. We can't have that happen, right? So why real time? Why do people want to do things in real time? One thing is definitely a better end user experience, right? So I think a lot of times the number one reason people want to move to these very low latency real time systems is more sizzle than steak. It's the ability to see something cool. Hey, this is really neat. The numbers just keep moving on the screen continuously as events are happening, right? It's sexy. People like to see that. You may not actually be able to make a human decision based on that data, but it's appealing, right? And that's not to be ignored, right? It's a kind of user interface benefit. Another kind is for operational intelligence, right? If you're actually looking at things happening in a system, if you have some kind of a security alert or some kind of a significant issue going on, where you don't want to have any delay in being able to see what's happening. So there's cases where people want to have a very accurate set of data at the moment that something is happening, which could be for analyzing things or understanding what's going on. The other thing is, that people will sometimes want to have real time in a more of an automated way, right? In fact, I generally think that most of the cases where you want to have some kind of near real-time system is going to be are ones where you don't want a human involved, but you want a robot, right? If you're really trying to respond to stuff super low latency, you probably want a robot that's in the system and acting as events happen, right? So, if you are changing your strategy for advertising, you probably want to change it very quickly once you realize that something's working or not, or you want to have an ability to make recommendations, right? There's a lot of these kinds of cases where as stuff happens, you want to be able to automate a response, right? So where you can, having closed loop automation in response can be great. It's not a panacea. As we've seen in one of the places where this has been pioneered on Wall Street with trading strategies, when we got robots, program trading systems trading, you had a lot of instability and a lot of flash crashes and a bunch of unanticipated effects in a system where everything is robots. But nonetheless, the net effect is an increasing amount of automation. And I think with big data, you're seeing that same trend pass into a lot of other areas, whether it's content recommendations or social scanning or advertising auctions online. So, why do people use Storm for this type of stuff? Well, it's a scalable way to manage reading queues and logic pipelines, right? So it's a lot better than, prior to Storm, people who wanted to do this had to build a complex distributed system, right? So it's kind of an analogy of MapReduce itself in Hadoop, right? But before that, if you wanted to build a distributed system to do batch processing or micro batch processing, you had to justify the cost of building and debugging a whole distributed system for one problem. And there weren't a lot of problems that were worth making that investment. Distributed search engines, it was worth it to build a search engine, but not a lot of other things, right? So in the same way, as you get into the real-time space, it's a lot easier to afford to build an application for a well-tuned distributed platform than to build a distributed system from the ground up, right? So that's the basic thing. And you've seen those benefits in the sense of, there's a lot of work has been done on reliability in Storm, ability to have tunable guarantees of messages and fault tolerance with certain constraints. It's been tuned a lot for speed, latest tests. I mean, there's lies, damn lies, and benchmarks, but generally, there's been certainly a lot of promising tests that we've done and others have done. Most recent versions of Storm, in some cases, getting over 1 million messages per node per second, based on a lot of tuning and identifying of scaling bottlenecks or latency bottlenecks, replacing the messaging transport underneath, these sort of things. It scales to a good degree. It's been scaled out into real-world systems at pretty massive scale, so it works well. It's got a thriving open source community, and more recently, it works on Yarn. So these are some of the reasons why people like using Storm, right? It's got a lot of these benefits. It has a lot of options for programming. While it's implemented in Clojure, I think it's got an intuitive, reasonable to work with Java API. So if you use Java, as a lot of organizations do, especially in the big data space, it makes it easy. It's a little low level, dealing with tuples and raw computations. But it also has a higher level domain-specific language called Trident. It gives you more SQL-like or peg-like primitives for working with data. So it gives you a higher level of abstraction, including the ability to work in batches of tuples, right? So you have things like joins and Trident to make it a lot easier than having to build stuff at a low level out of a raw API like a MapReduce API. And then there's a lot of other options, right? If you use Python or Scala, Clojure, Ruby, etc. There's a bunch of different ways that you can program Storm, so that's a nice thing too. So with that, let's segue into just some example use cases. We'll go through these. Some that come to mind are being able to have an analysis pipeline that's running in real time. You want to have data about what's going on across a lot of events, and you want to be able to scale that up so you can use a number of machines to compute it. That could give you live statistics. You might, in certain cases, use it for making recommendations to be able to update state in a distributed way, or predictions. Also, online machine learning, which is a generalization of recommendations. We talked about RPC. So let's delve into some real-world examples. So here's one application that we built for a customer where this was in the advertising technology space. We had we had a company that had a business model of making it possible to dynamically price content. And so there were a couple of elements to the system. One was being able to deal at the top. You have the flow for at the moment events were happening as content was coming in. You could keep track of those events. You could queue them up, and this was actually done on Amazon Web Services using simple queuing service. The Storm would dequeue things, do a little bit of bot filtering in real time, bucketize things, cache counters in memory. It wasn't critical in this case. This was often the case that you had exactly every event captured, right? So if you lost things in memory for a small amount that were being collected, it was okay because you have large numbers of page views, and if you were off by 0.01%, you didn't really care. It wouldn't affect the pricing algorithm in a meaningful way. So it also had performance counters as well. So this data is all being processed in Storm. And memcache was being used to manage the memory state, right? So again, remember, Storm doesn't do a lot for you around state. So in order to make it easier to share state among the nodes, partly because of the cost of using DynamoDB, which we were using on Amazon for our NoSQL database, it was being cached in memcache, and then it periodically flushed, think a few times a second. The performance counters and impression buckets would be flushed to NoSQL. Performance counters being things like clicking on ads, and then impression buckets, how many times people saw the pages. This data was all eventually synced out to distributed file system in Hadoop, so that you would have an archive, and in Hadoop, you would do longer-term analysis of this data, right? So this is a common flow. It's related to what Nathan Mars would call lambda architecture. It's not exactly lambda architecture, but very similar set of patterns, right? So capturing the data where you can then say in an offline way, hey, let's do our modeling to predict how likely it is that you'll get a certain number of page views, right? So the big part of this pricing algorithm was you were buying the ability to have a future of, I want to place an ad on a given piece of content, and I want to know what I'm going to pay to take control of this page and have all the ads for the next month that I own. So the system was designed to say, well, let's predict what the value is. So if somebody wants to come in and the ad sales system and buy it, we have to know how much it costs, right? So on the one side, we're updating in real time the events, especially as new content comes out. As you're seeing the events, it's critical to be able to update your prediction. And on the other side, though, you want to continually improve your model to say, if I've seen this kind of activity in the past, what does that mean, right? So you want to tweak your parameters. So we were using R, crunching the data in Hadoop, training a model in R that had parameters, and then the variables for any given page were stored in this NoSQL database. It was being fed by Storm, and we would create a prediction so that we would give it a real-time price. It would update it whenever events were coming in. So that's how we were integrating Storm and Hadoop together for this system to be able to both serve pages, sell ads, and predict the value of those ads. So another slice. Think about this is a different problem where we were actually working on taking smart meter data for a customer and saying, how would you use Storm for this, right? So we're feeding in data from the meters, which is a pretty large scale, real-time processing system where, again, you'd like to know if there's problems or issues that are happening based on patterns, maybe spiking demand, to, again, be able to do something like a prediction to say, are we going to run out of capacity? Do we need to go out to some of our customers and ask them to turn off or cut back on their power usage so we don't have a brownout condition, as well as things like trouble tickets that are indicators and geographic data, financial data, right? So a lot of this data is being ingested, and in this case, there's a dual path. There's a real-time path for real-time response where you want to make immediate decisions on a machine learned model. But again, the data is being fed into Hadoop for a longer-term processing and aggregation for long visualization and search. So you have the ability to have Storm for the near real-time analytics in this space and response, and then longer-term aggregation and analysis and search for data scientists in the Hadoop world. This is actually another slice of the first system that I talked about, which is being able to use more of a zoom in on how Storm was working, right? To be able to take in these impressions on ads, and what's being done is on the one side, in real time, the first bolt is simply stripping out bot activity. We didn't care about robots like Google's crawler. That wasn't, we wouldn't consider that worth anything for an advertiser. So removing those, and then one fork of it was actually adapting to write the data out in a durable way to DFS. Now, the reason we did this is we wanted to have a consistent view of what we were processing in real time and what we were storing in Hadoop, right? We didn't want to have bot traffic counted as being written to Hadoop any more than we wanted to process it. So we had consistent real-time filtering and lightweight annotation being done in Storm. And that's a pattern we've seen in a number of places where if you want to do things like another customer, we wanted to do something similar where for privacy constraints, we wanted to strip out or map exact IP addresses for Europeans out to mask out the low 8 bits so that we wouldn't have personally identifiable information. Again, using a system like Storm gives you a natural hook point to have that logic that as that data is flowing through, you can do that lightweight transformation and take that data out so that, for example, you could then ship it to a common place where you would have a Hadoop cluster that held the data for all your data centers. You can't ship that kind of PII from Europe, so you have to strip it in some real-time way. So a similar kind of pattern, right? Some transformations that are going on to have a consistent view of what you're handling in real time and what you're writing out into your Hadoop cluster. But then zooming in, what we're exactly doing was we had a bolt that was really bucketing these impressions by time series, right? So rather than looking at a discrete set of all events, our model trained on, over the last, minute, how many impressions were there, and over the last 5 minutes and the last hour, and so forth, right? So we bucketed over a zooming out range of time, and that was then stored for updating into the NoSQL database, which then was again fed into the real-time predictive model that got scored. So I'm not going to spend as much time talking about what's going on below, because that's less about Storm and more about doing data science inside Hadoop. It's complementary, but not the focus of this talk. So, the high level of this is, the solution approach was you take the massive historical data set for all the activity, the advertising activity and content viewing activity that has happened, and you pre-compile that to have a training model and a propensity model for each individual item, and then you update it with a delta for what's been happening recently to come up with your real-time prediction, right? So you continuously are taking stuff that was in the recent past, and it's being updated to your batch model of what happened, in the more distant past, and then you reset your recent past model, right? So that way you have the ability to keep a system that's consistent. It also makes it more resilient if you have small failures or inaccuracies in your real-time system, which is common. That you have a stable, consistent historical view that doesn't tend to diverge. So that's the general model. So in this case, we had our historical data was actually being stored in S3 for long-term storage, so mirrored from what was being stored transiently in the Hadoop cluster in DFS, and we do the analysis with Hadoop, Pig, and R. So Pig would run on Hadoop to pull out of the big data set smaller amounts, and then R would be used to build trained machine learning models, and then they'd be scored in the real-time system using R, the web service that was being called from our Storm system with NoSQL database, in this case DynamoDB holding state. So that's an example of a Storm-based system. But other examples of things you can do. Here's another case. If you think about doing recommendation updates, the classic example of this, and I like to bring this one up just because sometimes people say, well, Storm is a real-time technology, so do I need to use Storm anytime I've got any kind of a real-time response? The answer is really no, right? There's a lot of use cases where you don't need that level of complexity, right? So if I just want to make recommendations, I can have similar patterns to what I just showed you. I don't need anything as complex as Storm, right? So I might have a web server that is collecting events for a user on an e-commerce site, right? And so they come in and they look at some products and they buy some things. And I've got a batch feed. I could use a variety of techniques. I could use Kafka. I could use ship log files to a buffer server. There's a lot of ways I could get those events from my web farms into a Hadoop cluster. And inside the cluster, I can do the same kind of machine learning. I can train a model that says, what are the features that matter here? What are the kinds of weights I should put to say, how likely is it that the person will be interested in this particular product, right? I might do collaborative filtering or a bunch of techniques, right? And eventually I'll have a feed that maybe every hour or so I update a NoSQL database with everybody in the system. I've got 10 million customers, and I have a model of what kinds of things are they interested in. Then when they come in, they start browsing. I'm again going to tune that model. I'm going to use the NoSQL database to say, hey, for this user, what are they interested in? Well, that's interesting. I thought they liked sporting goods, but right now they're on a web page looking at music. So I guess they're interested more in music right now, and I'm going to make an update on that model on the fly. So I'll update the NoSQL state for that person, as well as having a batch event that will update their long-term propensity, right? So in this case, they're reading and writing a profile record. It's a low-cost order one computation. It's not that expensive, right? So you can pretty straightforwardly address this problem in real time with just any kind of a scalable NoSQL database and some kind of interface to do batch updates from your models that get updated in Hadoop to refresh that database. Some NoSQL databases are better at that, others are not as good, but it's been solved and it's a common technique. So this is actually, in my mind, by far the most common pattern that we see when people start integrating real-time response into a big data system. No Storm required. When you can get in and start using Storm. Actually, I'm going to skip over this slide. because I think it's a little repetitive. But you know, let's get into at this level why might I want to use system, right? And it really gets to if my updates are starting to be more complicated, right? If I wanted to do things like a real-time collaborative filter update where I wanted to take many people that are closely associated with this person and update all of their interests, then I might have a lot of updates of state to make, right? So a case of this might be if I had a certain number of influencers that we're expecting or driving, say, fashion tastes, and a lot of customers' behavior would be influenced by that, right? So think about like a celebrity tweeting about buying a pair of shoes, and all of their followers are much more likely to be interested, right? In that kind of a scenario, I don't want to have a single process, a single thread, updating thousands of followers' profile records to say, hey, they're more interested in this shoe, right? So in that case, I'll post an update to a storm topology that can then shard it out and distribute that update across many NoSQL database records for all these followers who are influenced by that celebrity and asynchronously do those updates in real time. So it can be a very similar model, but now the difference is I have a processing problem that is not a simple, hey, this one user is affecting one record. I'm now having a single event that could have a large amount of computation. And that example is also important that you typically see that these things are these long-tail distributions where there's a handful of cases where an event drives a large amount of processing, but most events do not, right? So the average person, if they buy some shoes, they've got 25 followers maybe that would care, and it's a pretty quick update. But the celebrity case, you have to think about handling it especially, right? So that's a kind of case where you might want to parallelize your analysis or your updates, and that's where suddenly having a system where you have the power of distributed processing really gets interesting. So that's a case where now I've got a recommendation engine where it made sense to have Storm involved. So, again, the other cases besides, those kind of network effects I might have a really costly multi-dimensional model, right? So there's going to be other cases as well where you could probably fill in ideas of where might I have a more complex model where I can have a lot of work to do in real time. So this is another example or a little more detail of how you might handle this. That again, you would have this combination of activities of information, the online profile, offline profile, and user activities that are flowing through a message queue with Kafka that then is being pushed into the Storm system for that real-time processing. I might also be doing things like pushing it into Elasticsearch so I have some events to process. This could be related. I want to be able to have the ability to quickly look up what's going on with users and their state here as well. So let's shift gears from consumer behavior online and go back to the energy management case. You might a little more detail on using Storm in this case. In this case, we could use Kafka to ingest real-time events like the meter or sensor data from a smart grid, to pull in geo information, or weather data, or real-time disturbances like lightning strikes, or potentially earthquake data. So there's lots of this kind of data that you could access that could be streamed in real time. As is often the case in big data systems, only one of these data sets is actually a big data set, which is the meter data, and the other data sets are relatively small, right? Weather data or aggregate energy production data, maybe forecast data, but you want to blend it together. So being able to distribute it out and connect it together so that you can have that enrichment of data is still powerful, right? So Kafka lets us ingest the data, and then in Storm we can process. So we can do stream processing to handle the data consistently and put it in a real-time update to a search engine, right? So if I put the data, if I process it, organize it with the lightweight transformations in real time, and then I load it into Elasticsearch, now suddenly I can have search results, milliseconds after an event happened that have joined in those interesting data sets. Or I can put them into Hadoop for archive and offline training. Or I can put those updates into a NoSQL database for being able to update my profiles. I'm out. Okay. Sorry. And I can also have, in this case, there may be some, again, some cases where my computations are expensive, right? So predicting grid stability or market prices, these are types of things where I have lots of events feeding in, but I may have a fair bit of computation to do that I need to distribute out. So I have large amounts of input to compute certain really important variables that I have a lot of computation to do, where a streaming system like Storm lets me have always a real-time predicted price or stability metric that I can feed in a lot of data and handle it to have a threshold and say, do I need to publish out an alert or a warning that, hey, the system is, the grid stability is declining, we're hitting near a peak of capacity and we need to take some action to avoid a brownout, right, that kind of thing. So another use case for Storm, somewhat related, is in the finance arena. So here, what we'll see is feeding the market data, so tick data, order book data, large amounts of data about all the trades that are going on in the market. The first thing you will do with Storm is collecting that data will boil it down, so distilling out more essential data, what's high and medium and low frequency, so condensing it to a more usable pattern in real time. So again, a little bit like the time bucketing that we talked about in the advertising example before, which then, when certain patterns are hit, then it becomes worth drilling deeper and saying, hey, this has hit a threshold that I want to do more expensive computation, pull a bunch of data from a NoSQL database and start doing a deeper analysis to say, hey, is this a potential compliance violation? Is this showing patterns that it might be risky, right? So it's kind of a two-level model, taking this massive maelstrom of data and basically taking 99% of the trades and saying, well, they're not very interesting, but the 1% that start to show some signals of being a problem, drill deeper and get a lot more information to run a more computationally intense model, again, distributed, so that you can decide which ones really needed to be investigated or triggered or flagged as an issue, right? So this is a way of doing compliance monitoring for trades with market data using Storm. So this is a lot of words that say something similar. In the bottom, I think one thing that's interesting is this was about a year ago, actually, we did this benchmark for a large financial information provider that they were looking at a costly commercial software, and the per machine performance at the time of Storm was about half of that of the costly commercial software. But when you consider the price of that software, the total cost of ownership had 25 times better price performance with Storm than with a commercial software package that's certain blue company likes to sell into Wall Street. So just a few more thoughts here from those use cases, and then we'll put it open for any questions. I think what we found is that it can often be easy to develop with Storm, but it can be hard to debug, right? That it's still a system where it's a real-time distributed system, and when things go wrong, it can be a bit challenging, right? So you often will start, as always, with can you get the system working well locally, right? I mean, so we had problems with timeouts in one of our projects we're doing with Storm, and if you can recreate it locally, it's a lot easier to resolve. But if you really have distributed interactions that are unreliable, it can be a fair bit of work, right? So while Storm gives you more predictability and its core is well-tuned, it's a lot easier in a distributed system to have things go awry and to have problems, right? We had a case where we had an infinite loop of failures, right? So that was one of the things actually we used Memcached for, was we would have a bad input would come into the system, and it would fail, we'd reject it, and then we'd try to reprocess that same bad event, right? So if you have a bug in your code or bad data that triggers a chronic failure, you'll just keep retrying the same message, saying, well, it's failed. So in that case, we actually had a way we used Memcached to count things and keep track of repeated failures so that we would eventually, finally, simply fail something and say, I'm not going to retry this. I just think it's a failed thing. I'm going to say it's done and put it in a failure queue that I can look at later, right? So that was something we ran into. The reality of, if you're working at single events at a time, you have at least once processing will mean you'll get duplicates, right? So we one pattern you can use for addressing that is to have a read repair job where you deduplicate events, right? So maybe you'll live with the occasional duplicate. Hopefully your system doesn't have lots of failures, and a failure is an occasional event. So your real-time processing will be slightly off, but then when you're persisting the data in a durable way in Hadoop, you'd like it to be exactly right, and you'd like to compress out those duplicates. So that's easy if you have an exact unique identifier you can write with the data. If you don't, it gets harder. We had cases where performance counters weren't getting flushed properly, so we had the notion of having artificially, periodically a tick, a time epoch going through the system that would be a cue to say, so the issue was, hey, we might have a long tail content here that we had a rule that we didn't want to write out every time an event happened in a single database. We wanted to cache it, but we would say, well, every 1,000 events we'll flush it to NoSQL. Well, that's great for the high frequency things that are going all the time, but if I have a page that's not getting a lot of page views, I might be holding that state for hours, right? So by having something, we implemented ticks that would flow through the system and be a trigger to say, when I get this type of event, it's not something to count, it's just a signal that time has gone by, you need to flush now, right? Also, from a programming standpoint, you always want to acknowledge in Storm. It's a better practice, and there's no cost, and it makes the system more reliable. And again, with at least once processing through batching your data to durable storage, whether it's Amazon S3 or Hadoop's distributed file system, you had to run either a compaction or an event dedupe job, or if you're doing micro batch, you might get away with using Trident, and it's exactly one semantics. It puts a little more overhead in and managing its own state durably, so it knows whether stuff's been processed, but it makes life easier downstream. And the other thing that we noted was that when we had different time frames, we would actually found it beneficial to have different queues for processing things at different time scales between collecting stuff for milliseconds and minutes. We'd have a different queue to feed into different topologies. So even if it was the same data, we'd have different queues because we had different cycles of processing. So those were some of the lessons from some of the first projects we've done with Storm. So in conclusion, I'd say there's a lot of different kinds of real-time problems. Sometimes using Hadoop and or NoSQL, and Hadoop's version of NoSQL HBase or other NoSQLs can solve these, right? So there's a lot of places where you can take state and partition it locally and have a low cost lookup, read and write behavior where you don't need to distribute the processing. So there's a lot of those types of scenarios where you don't need something like Storm. Storm is valuable in the more complex cases. You've got real-time distributed logic. You want to do some distributed transformations, scrubbing, modification of data, both for real-time updates into a database and for collection for longer-term processing, operational intelligence, right? So I think as we build more, and then the last thing I'd say is that it's crawl, walk, run, right? That Storm came about a few years after Hadoop for a reason. Once organizations were getting their arms around doing more offline processing in Hadoop and starting to do some simple machine learned models and using NoSQL to serve those out to endpoints, then they started to see all the use cases for more complex distributed models. So if your first big data technology, if you're thinking about what your first big data technology is going to be, it's probably not going to be Storm. It'll probably be Hadoop. But as you get more sophisticated and you start saying, hey, we're really good at this Hadoop and NoSQL stuff, and we're seeing more complex problems, Storm's an excellent thing to take a look at. So those are just a few thoughts on Storm and its place in the ecosystem. And again, we're hiring at Think Big. And with that, I'll turn it open if there's any questions. Questions in the back.
Can you talk a little bit more about the differences between Storm and Spark? I mean, very similar, I believe, right?
So the question is, can you talk a little bit more about the differences between Storm and Spark? And sure, I mean, there's some good talks on the internet that are all about that, right? So it's a hot topic. So Spark streaming is the part of the Spark project that is probably the most directly competitive with Storm. Spark is a way of processing data. It's modeled in many ways on MapReduce, but it has the notion of built-in the ability to have data being cached. Now they've tuned it so that because it's designed for it as an in-memory system, it can have lower latency processing, and so with that, it was reasonable to say, well, what if we started running really small batches of data continuously through this thing? Does it work? And the answer is yes. You can make Spark do these small streams of data and little packets going through chunks of a few records, right? So you wouldn't reasonably want to use Spark streaming to process a single event at a time. The latency would be too high. But in use cases where you're doing micro batch, it can be competitive. And there's a lot of cases, back to that slide, about, well, what's real time? If you have a few milliseconds of latency for a batch, there's a lot of cases where that would be perfectly reasonable. So in those cases, they are competitive. I'd say that there's a lot of elements to it, but I'd say that Storm is more mature, it's better tuned, it's more widely used in production. I think the advantages of Spark are probably that it's a common model, right? So you get a similar model whether you're doing batch processing or real-time processing, right? So that's an appealing element to it. And there's also differences in terms of commercial support from different vendors, right? So not all distributions, it's one of the many flashpoints in the ongoing battle between the Hadoop distribution vendors. Do you prefer Storm or Spark streaming? So, check your Hadoop distribution to see which one they support is often a factor as well, right? But the net is, I think, it's early innings, that this is going to be an interesting one to see kind of whether Spark streaming kind of catches up in maturity and its connection with a fairly popular platform, Spark, which is most popular for machine learning, for doing distributed iterative machine learning models. That's really probably the first place Spark's gaining traction. Whether that's going to kind of propel it forward to catch up to the head start that Storm has. Yeah.
So I have a couple questions. First one is, once you figure out the patterns and architecture of the system, how long does it typically take to code and put the system in production? And the second question is, have you had a business case or use case where you had to retrain your model in production? And if you did, if you had any technical issues having to do that, are there any limitations?
Sure. So how long does it take to put together a system? Well, I think it varies a lot. I mean, consultant answer, right? But it's true. What we typically do, well, generally, in building any kind of a big data system for a customer, we try to ship a first release in 8 to 12 weeks and do releases, every 8 weeks. That'll vary a little bit. For larger companies, that's about as fast as you can release things and kind of they can absorb change. When you get into smaller, nimbler startups, the pace tends to pick up and you'll do more frequent releases more rapidly. We use an agile method where every week we're doing a sprint and we're integrating code. So you can integrate things but not choose to release it. But that isn't totally answering the question. I mean, it's typically within a release you can get a core of processing up and running, and a lot of the complexity really gets to what's the complexity of your data, what's the complexity of logic, what's your minimum viable product, what's the least thing you can ship that's going to actually be useful, right? Those are the variables. So, I would say that oftentimes the first release after a couple months is it's sort of an alpha that you've got something up and you're now running in shadow production, and maybe the next release 8 weeks later you're now into having something that's really usable in production. It's a guideline, right? So that would probably be it. And with Storm, you're probably not going to be adding Storm to a system or using it until you already have some kind of existing big data architecture in place that's solving a use case that's a little bit simpler. And then the other question is, do you ever retrain machine learning models in production? And the answer is almost certainly yes, that things change, and one of the powerful things about machine learning is you can rerun your model, right? You can relearn, right? That it's not a one-time tuning. So I would think that it would be an odd system indeed where you didn't retrain your model.
So does the system have any limitations or technical issues having to do that? Maybe the size or?
So, I mean,
do you run into any issues?
A lot of, working with machine learning is an art, right? It's a science and an art, data science. Working with the data, there's a lot of things that you have to know in order to be good at it, right? That you have to understand overfitting and look at the data and think about what features come out. And, there's always room to improve models and think harder about how to get more signals. So there's lots of things that can go wrong, right? It's not a simple mechanical thing. You can't just take a look at SVM as a distributed machine learning library algorithm and say, okay, well, I'm just going to throw this at my problem, I'm done. It takes some sophistication and some knowledge around how to do data science well to condition the right problem and get the right answer. Yeah.
Talk more about the reason why you say that Trident is better fit for batching.
So I was saying that Trident has a notion of running things in small batches, and certainly if you're going to run, if in Trident you're going to run exactly once semantics, the overhead of that is a much better fit for running in micro batch than single record at a time. If you dial your micro batch down to one, a single record, you're going to have basically an I/O operation to persist and checkpoint the state for every record, which is going to dominate the cost of processing events. So you wouldn't normally want to do it for a single record at a time. That doesn't mean you couldn't use Trident. I mean, if you didn't use it for exactly one semantics, there's no reason you couldn't use Trident to do a single record at a time. But I'm just saying the way that exactly one semantics is implemented in Trident, you won't want to use it for a single record at a time. Yeah.
Just two questions. Now that Teradata has Storm, are they going to keep the source code, that you guys are doing the consulting for that? And then the other question is, somewhat of the connection of workflow, we can do R and use that as Hadoop, but that's got to be a manual process, or is it automated and then pushed into the Storm stream and everything, so it updates models?
All right, so let me start with the sort of what's behind the first question, right? So, and Think Big, we're continuing to work on a variety of platforms, right? So we don't just work on Teradata technology. Teradata does sell an appliance that has Hortonworks distribution for Hadoop on it. The latest version of that appliance, I don't believe has Storm because it's just coming out in the latest Hortonworks distribution. So it's not exactly right to say Teradata has Storm, right? We at Think Big have worked with customers using Storm on projects. And we're going to continue to work on what makes sense for the customers in open source, not just specific technology that Teradata sells and supports. So that's the first thing. I had to start with that. Now your second question about Storm, can you state that again?
Yeah, just look at your models you had. We're going to use R. I'm familiar with R, and using that to create the predictive models. If we're going to do iteration machine learning, whatever you do. But it wasn't clear to me in the diagrams whether that was an automated process or that was somebody manually doing the updates, and then someone manually doing the code, maybe using Python. You were thinking Trident. I guess that's maybe what you guys are using, and to do the updated models after the learning we've done. Yeah.
So good question. So the basic life cycle was to write the code in R that would both do the training and scoring. The code that would work with that was written up front, but then including what are the ability to work with a variety of different features, right? And so once that's done, it's being run in an automated way that you're continually retraining. You're not writing new code for that retraining. You're running the same training and scoring code, training it in batch, scoring the deep history in batch. I mean, maybe it's worth going back to the diagram here just to emphasize or explain what I'm talking about. Here, right? So what's going on is over here, you're doing training on this historical data set. You're running predefined R code that takes the historical data and the supervised training, figures out what is the weight of various parameters. Then you apply that model more frequently to score history. So for each piece of content you score its predicted value, and based on historical behavior. But then the same R code is then used to update that score with the most recent historical data, right? So shifting it back in time and then adding in the most recent events in the time series to update based on that model. And again, it's actually the same R code that's running. It's just a delta update over here. So the code is the same, but new events just change the coefficients, right? So you can change that code if you want to change that code. So if you want to optimize and improve your model, you can say, hey, I've got a great idea for another thing that's going to make my model better. It's more predictive. I've got a new way of coming up with signal, maybe some new data or a new way of creating a feature out of the existing data that's going to make it a better model, and then I can test it out, maybe do an A/B test and compare the two. But I'm always going to be running kind of a common set of code and have automated processes to train it and score it in batch and score it in real time. Yeah.
out of the use cases you outlined, which one do you feel the strongest about, and where do you see the biggest adoption and change happening in the near future? And is online consumer behavior, dynamic pricing, and content a piece of that or not?
So the question is, of all these use cases, which one do I feel the most strongly about? I mean, I think that probably operational intelligence, so the ability to kind of see events that are happening in a system in near real time, where you've got more complex processing, or you've got some filtering going on, is probably the most prevalent one that I see. And I honestly think that it's more, the value there is a little bit more eye candy than kind of solid business value, that people like to see a real-time chart of all these statistics populating moment to moment instead of having an update every 5 minutes. So I think that's probably the reason that people are most adopting it. Now, it sounds like I'm not super excited, because it's not as much, honestly. I mean, the value is a little bit more superficial, but I think that's probably the most. I don't know, who here has actually deployed Storm in production? Who here has deployed Hadoop in production? Okay. Anyway, so there you go. Infinitely more Hadoop adoption than Storm adoption. All right, thanks. Yeah.
So there's a component of actually writing the software, and then there's the component of actually deploying it and maintaining the actual deployment as a DevOps. What would you say the which one is the biggest?
Yeah, so it's a good question. Between the effort to develop the software and deploy it and maintain it, DevOps, which is the biggest effort. And again, I think maintaining Storm is still complex and costly, right? It's an excellent point that developing it is not always so bad, but it's sort of the point. Well, if it was hard to debug, then when weird things happen in production, you got to debug them, right? So in practice, now, more recently, we're starting to see some of the benefits of having Storm integrated in with Yarn and having Umbari for management. So you're starting to get some better tools for DevOps, but it's still years behind Hadoop. It took a long time for Hadoop to start to get better management tools that made life easier for DevOps, and it's certainly not all the way there that it's a simple turnkey system to operate, right? So Storm is a lot less mature, and it's also a little bit harder in the sense that in an inherently batch system, it's a lot easier to recreate things and replay them, but it's really hard if you have something go wrong in a Storm system. It can be very challenging to say, how do I recreate that problem, right? So how do I know if I've got intermittent issues going on, what's going on? So, part of it is also you want to design for manageability and built-in things, so you have the ability to get data out of your Storm system and debug it and have counters. And so some of it you have to design it in, but it is more challenging to operate.
You have numbers on the percentage of effort spent on software development?
It's a good question. I don't have a statistically significant sample to tell you. So a lot of times too, we more recently have started helping our customers on the DevOps side and managed services and application support, because we see that, just like to your question, as people find challenges in developing these systems, they find challenges in operating them. But honestly, prior to the last 6 months, we really, our mode on DevOps was more to give our customers run books, to guide them on how they should operate the system, and then their IT departments would take them over. And we just didn't get a lot of data from them, right? Other than, if we were continuing to work with them on development and something raised its hand as something they needed support on. Yep.
So what happens if you overload Storm? Don't use any message queues, don't use captains. Overload Storm, what's the behavior?
So what happens if you overload Storm? Well, I mean, it's an interesting caveat. You say, well, what if you don't use a message queue? So, I mean, I guess I'd say, well, what are you using to feed Storm at that point?
Something that's feeding like a lot of messages.
Right. So, I mean, so it's probably ultimately, Storm will only drain whatever queue or stream of events are coming in at the rate it's able to process. So, if you have a greater rate of incoming events than that, there'll be back pressure that the upstream queue will have more and more things if it's being set up to queue them, right? So you could configure your upstream queue to drop stuff, right? If you said, well, I'm just going to have a limit on how much history I'm going to hold, and if my downstream consumer can't process it fast enough, it'll just start dropping things, right? So I mean, it's that actually isn't a storm question per se, but it's a question about your upstream system that's delivering events to storm, your spout, as to how it's going to behave when it's not having its events dequeued quickly enough. Yeah.
So you said that Storm doesn't have support for state much, but Trident does, doesn't it?
Trident has, so Trident has some notion of state. It has it has ways of managing state for things like, have I processed this batch? But I still think it's a fairly low level of notion of state. It's not integrated in to the processing in some deep way. I mean, so there is some notion of state in Trident, but I think it's still a low level version of state.
I'm thinking about persisting aggregated data to Cassandra or something like this.
So you can integrate in an external system like Cassandra, a NoSQL database, to manage state, but that's still pretty loosely coupled, right? I mean, it's like, again, the application, I can use an external service to manage state, but it's not in any way connected with my logic and my flow, right? I can't sort of naturally say, oh, when I partition this data, I want to have every one of these things have a kind of a correlating set of state in this way. So I still feel like it's, that's just, I guess, more opinion, but I feel like it's still fairly coarse. They're pretty fairly loosely coupled, not well designed together abstractions. But that's a high level statement. But it doesn't have its own built-in. It's relying on some external service that's kind of an interface. Yeah.
And to follow up on that, then what are people doing? Put a proprietary system solution or programming in, or are they just letting it go? I mean, if state's lost, it crashes. Oh well, we just keep on going when it comes back.
So what are people doing? Well, what they do is just more of an application concern, right? More of the work of using state for something like NoSQL in your distributed processing falls on you, the programmer, right? So I guess my argument is that it's still a fairly low level of abstraction. You can solve the problem, you can build the system, but it doesn't have the patterns and idioms you might want. It's not as simple to manage state, right? You can do it, but you're working at a lower level of abstraction.
We'll just do one more question.
All right. Or not. Well, thank you. Oh, we have a last question in the back.
This is probably a naive question. Why would you want to do the offline, the batch processing, if you can really do real time?
So why would you want to do offline or batch processing if you can do real time? Well, I mean, I think it all comes down to, like I said at the very beginning, right? If real time were free, why wouldn't you want things with as low as latency as possible? But it's never free, right? It's more costly in terms of resources, the more costly programming model, it's more costly DevOps, right? So you have to make trade-offs of what's the right amount to invest to drive down latency, right? And make a decision based on that. So it's not free, and you have to balance the benefit of lower latency with the cost. All right, well, thanks, everyone.
Just a few quick things. We want to be good just factual. So I was hoping, if you don't mind, if you can clean up yourselves. Also, we want to put back the chairs back together. I'll just be putting up a picture right now of how the tables and chairs should look like. So if you don't mind just taking, spending a few minutes and putting that up, that'll be great. And with that, I'm going to raffle off some books. Ron, if you don't mind picking up.
Sure.
Does anyone need raffle tickets? Before we get... You can come up here and pick them up.
I mentioned a raffle when I came in.
We got it.
Hey guys, we're going to raffle off the books now.
Yes.
All right. How many books do we have to give out to it?
3 books and 2 questions.
All right. All right. Vote early and often. Always the rule. All right. So what are we going to start? We'll start with a book.
Yeah, Hadoop book.
All right. This is for a Hadoop book. And it's 714-337. 714-337. All right.
There you go.
Thank you. Congratulations, Sean.
Thank you.
Now,
All right. Oh, thanks. Thanks for coming. Next up is anonymizing health data. And the winner is 714-349.
So close.
349.
They're going to remain anonymous. Oh, here we go. Perfect days. How's that? Congratulations. All right. And get the scoop on scoop. So it's 714-325. Nope. All right. Nice work. Lenny, thanks for coming. Congratulations. All right. And we've got 2 Big Data Now books. So the first winner is 714-350.
I'll take it.
If you're just bold and come up, maybe they won't check, right? Do we? We'll put it aside and we'll try again. All right. How about 351? 714-351. All right. Srinath, congratulations.
At the side. Those are at the side.
And the other, we have another Big Data Now book, which is 341.